elaborate on evaluation metrics and feature engineering, which are two of the most critical steps in the machine learning process. Step 5. Deep dive, evaluation metrics. Evaluation metrics are essential for quantifying the performance of your trained model, especially on the unseen test set. The choice of metric depends heavily on the type of problem, classification versus regression. 1. Classification metrics for predicting categories. These metrics assess how well the model assigns instances to the correct class. Confusion matrix, a fundamental table that summarizes the predictions versus the actual values. It defines true positive, TP, correctly predicted positive class; true negative, TN, correctly predicted negative class; false positive, FP, incorrectly predicted positive, type 1 error; false negative, FN, incorrectly predicted negative, type 2 error. Accuracy, the most intuitive metric, the ratio of correct predictions to the total number of predictions. Caveat, can be misleading in imbalanced datasets where one class is much more frequent than the other. Precision, of all instances the model predicted as positive, how many were actually positive? Measures the quality of the positive prediction. Recall, sensitivity, of all the actual positive instances, how many did the model correctly identify? Measures the ability to find all positive samples. F1 score, the harmonic mean of precision and recall. It's a single score that provides a good balance between both, especially useful in imbalanced scenarios. 2. Regression metrics for predicting continuous values. These metrics assess how close the model's predictions are to the true continuous values. Mean absolute error, MAE, the average of the absolute differences between the predictions and the actual values. It's robust to outliers. Mean squared error, MSE, the average of the squared differences. Penalizes large errors more severely than MAE, making the model sensitive to outliers. Root mean squared error, RMSE, the square root of the MSE. It's often preferred because the result is in the same units as the target variable. Step 3. Deep dive, feature engineering. Feature engineering is the process of using domain knowledge to create new features, input variables from raw data to improve the performance of a machine learning model. Goal, to make the data patterns more explicit and digestible for the learning algorithm. Techniques for feature engineering. Decomposition/extraction, breaking down complex features into simpler ones. Example, splitting a date column into 3 separate meaningful features, year, month and day of week. Aggregation/combination, grouping or combining multiple features. Example, calculating the average number of customer transactions over the last 30 days and adding it as a new feature. Example, creating a ratio like price_per_square_foot from price and square_footage. Discretization binning, converting a continuous numerical feature into a set of discrete categories, bins. Example, converting age, 25, 33, 41, into bins, young, 18 to 35, middle-aged, 36 to 55, senior, 56 plus. Handling categorical data, encoding. One hot encoding creates a new binary, 0 or 1 column for each unique category. Label encoding assigns a unique integer to each category. Be careful, this implies an ordered relationship that may not exist. Handling text data, vectorization, converting text into numerical representations. Example, term frequency, inverse document frequency, TF-IDF, or word embeddings, to capture the meaning and importance of words. We have covered the machine learning process, evaluation metrics and feature engineering. A logical next topic would be to delve into model selection and training SAES, specifically focusing on the different types of ML algorithms. Model selection and algorithm types. 1. Supervised learning. This is the most common type of ML. The model is trained on a labeled dataset, meaning the input data already has the correct output assigned to it. Goal, to learn a mapping function from the input features, x, to the output label, y equals f of x. Key tasks. Classification, predicting a discrete label or category. Examples, spam, not spam, fraud, not fraud, cat, dog. Algorithms, logistic regression, support vector machines, SVM, decision trees, random forest, k-nearest neighbors, KNN. Regression, predicting a continuous output value. Examples, house price, temperature, stock price. Algorithms, linear regression, lasso regression, ridge regression. 2. Unsupervised learning. The model is trained on an unlabeled dataset. The goal is to explore the data and find hidden patterns or structures without any predefined output. Goal: to infer the natural structure present within the data. Key tasks: clustering, grouping similar data points together. Examples: customer segmentation, grouping documents by topic. Algorithms, k-means, DBSCAN, hierarchical clustering. Dimensionality reduction, reducing the number of features while retaining most of the important information. Examples: data compression, visualization of high-dimensional data. Algorithms, principal component analysis, PCA, TSNE. 3. Reinforcement learning, RL. The model, an agent, learns to make sequential decisions by performing actions in an environment to maximize a cumulative reward. Goal: learn the best policy, strategy to follow by trial and error. Examples: training autonomous vehicles, playing complex games like chess or Go, robotic control. Key concepts: agent, environment, action, state, reward. Key decision factors for model selection. 1. Problem type: is it a classification, regression, clustering, or optimization problem? 2. Data size and complexity. Small linear datasets might use linear regression, while complex large datasets often require deep learning or ensemble methods like gradient boosting. 3. Interpretability. Do you need to explain why the model made a certain prediction? Decision trees are highly interpretable, or is predictive accuracy the only concern? Neural networks are often a black box. 4. Training time. Some models, like complex neural networks, take significantly longer to train than simpler models like logistic regression. Interpretable part of supervised learning. Deep dive decision trees. A decision tree is a non-parametric supervised learning algorithm used for both classification and regression tasks. It essentially models decisions as a flowchart-like structure. How they work. 1. Splitting. The tree starts at the root node and divides the data into two or more homogeneous subsets based on the most significant differentiator among the features. 2. Decision nodes. These nodes represent a test on an attribute, e.g., is age greater than 35? 3. Branches. These represent the outcome of the test, e.g., yes or no. 4. Leaf nodes, terminal nodes. These nodes represent the final decision or prediction, the class label for classification, or a continuous value for regression. Key concepts in tree building. Purity. The goal of splitting is to make the resulting subsets as pure as possible, meaning they contain instances of primarily one class. Impurity measures for classification. Gini impurity measures how often a randomly chosen element from the set would be incorrectly labeled if it were labeled according to the distribution of labels in the subset. Lower Gini is better. Information gain entropy measures the reduction in uncertainty entropy after a split. Higher information gain is better. Advantages. Easy to understand and interpret, the logic follows human decision making and is highly visual. Requires little data preparation, they don't require feature scaling or normalization. Handles numerical and categorical data, they can work with both types of features. Disadvantages. Overfitting. Decision trees can easily overfit the training data, capturing noise and resulting in poor generalization to new data. Instability. Small variations in the data can lead to a completely different tree being generated. Ensemble methods, boosting tree performance. To overcome the instability and overfitting issues of single decision trees, we often use ensemble methods, OOF, which combine the predictions of multiple models. 1. Random forest. Mechanism. It builds multiple independent decision trees, a forest, at training time. Each tree is built using a random subset of the data and a random subset of the features. Prediction. For classification, it uses a majority vote from all trees. For regression, it takes the average of all tree predictions. Benefit. Reduces the variance and overfitting often seen in single trees, leading to much better generalization. 2. Gradient boosting machines, GBM, by XGBoost. Mechanism. This method builds trees sequentially. Each new tree attempts to correct the errors, residuals, made by the previous tree. Key idea. Boosting. Weak learners, the individual trees, are combined to create a single powerful learner. XGBoost, a highly optimized and popular implementation of gradient boosting, known for its speed and performance in competitions. Benefit. often achieves state-of-the-art predictive accuracy, though it's less interpretable than a single decision tree.